how it looks, a resonance. You can see it basically in the phase shift, a great increase of the phase of almost magnitude pi over a very small change of energy. And it should come accompanied with a very big amplitude inside. So this is how it looks, and I want to now proceed after, if there's some question, on how do we search for resonances a little more mathematically rather than plotting them. How could I write an equation for a resonance? I cannot say, oh, the phase changes fast. Well, that's not a very nice way of saying it. It's good, it's intuitively, but we should be able to do better. So how do I find resonances? So let's model resonances a little bit. How do we find resonances? So let's model this behavior. By that is writing a formula that is simple enough that seems to capture what's happening, and that formula is going to inspire us to think of resonances perhaps a little more clearly. So suppose you have a resonance near k equal alpha. I claim the following formula would be a good way to represent a resonance. We would say that tan delta is equal to beta over alpha minus k. Or, yeah, we could say that tan delta equal beta alpha minus k. Or if you wish, delta is tan minus 1 of beta over alpha minus k. Why is that reasonable? It's a little surprising, but not that surprising. You see that when delta is equal to minus pi over 2, the tangent of delta goes to infinity. So there's something going on here in which you have this property. So let's plot this. So let's plot beta over alpha minus k to understand it. We need a plot to understand this. So this is k, and we're plotting this quantity. Well, it's going to go crazy at k equal alpha. That we know. When k is less than alpha, I'm going to assume that alpha and beta are positive. They both have units of k. And when k is less than alpha, you begin here, then this denominator is positive, the numerator is positive, ratio is positive. Is small, maybe, and then suddenly when k reaches alpha, it goes to infinity. Oh, it's going to be like that. Now, it actually is true that when k differs by alpha by beta, it reaches value 1. So here is alpha minus beta. That point, it reaches value 1. So if I want this thing to be very sharp, I need beta to be small so that it's little until it reaches beta within, distance beta within alpha, and then it shoots up. So I want beta to be small for sharp behavior. On the other hand, here, it goes the other way. It goes from minus infinity back to 0. And has value -1 at alpha plus beta. So within minus beta and beta of the center alpha, most of the thing is happening. If we plot now the tangent of this, or the arctangent of this, tan minus 1 of beta alpha minus k, well, if the tangent of an angle is very little, the angle can be taken to be very little. At this point, it will reach pi over 2. So the angle is little, we'll go to pi over 2, and then quickly becomes larger than pi over 2. You're thinking tangents. So the tangent is going up, it's blowing up at pi over 2, then continuously it goes to minus pi over 2, and then continues to go to 0, so it reaches pi. So this is the behavior of delta. Delta is this tan minus 1 of beta over that. And delta is doing the right thing. It's doing this kind of behavior. There's a shift. I could add a constant here to produce the shift, but it's not important at this moment. The resonance is doing this thing up to a total shift of pi that doesn't change the tangent of an angle. So this is one way of modeling what's happening to the phase shift near a resonance. So let's explore it a little more. I can do a couple of calculations. For example, I can compute what is v delta vk at k equals alpha. That should be a nice quantity. Is the derivative of the phase at the resonance, at the position alpha of the resonance. So here is delta, here is k, and there's the derivative of this k. And how should it be? Well, basically, the phase changes by amount pi over a distance beta, or 2 beta. So this must be a number divided by beta. You can calculate this derivative from this equation. It's a nice exercise. Try doing it. It's actually just 1 over beta. That's a result. 1 over beta. The other quantity that is nice to understand is how does the scattering amplitude behave near the resonance. So what is the value of AS squared? That's the absolute value of psi s squared, which is sine squared delta. That's the same thing as AS squared. Well, you know what is the tangent of delta? A little trigonometric play that you should be able to do it. It can give you the sine squared delta. And here's the answer. It's beta squared over beta squared plus alpha minus k squared. Kind of a nice, almost bell shape. Of course, it's a polynomial, but it looks a little like just a nice symmetric shape around alpha equal k. Now, this distribution is so famous that has been given a name. It's called the Breit-Wigner distribution. Breit-Wigner. But it's described as the Breit-Wigner distribution. And it's usually referred in terms of energy. Not momentum. So, and it's what should happen to scattering amplitude in general when you have a resonance. So the way to do this calculation now is to say, well, what is alpha minus k? Let's try to relate it to the energy minus the energy at k equal alpha. Well, this is h squared k squared over 2m minus h squared alpha squared over 2m, which is h squared over 2m k squared minus alpha squared. On the other hand, I have here alpha minus k squared. I don't have k squared minus alpha squared. So, approximations. If the resonance is narrow enough, if beta is small, let's do an approximation here. We do h squared over, everybody does this approximation, shouldn't be afraid of doing it. It's alpha, how would I write it? K minus alpha times k plus alpha. And the approximation is that, you know, all the interesting thing comes from the difference between k and alpha, how close k is to alpha. So when k is close to alpha, all the dependence is going to be here. This is going to be about 2 alpha when k is near alpha. And if it's a little more than that, it doesn't matter because it's subleading. So this can be approximated to 2 alpha. And therefore this becomes h squared over alpha over n times k minus alpha. So that's a little help. Then size of s squared, doing a little more of algebra with the constants there. Probably, if you want to do it, leave 2 lines. It's trivial. It's really simple. It's always written in this form. 1 over 4 gamma squared over e minus e alpha squared plus 1 over 4 gamma squared. And that's the so-called Braith-Wigner distribution. And gamma is a funny constant here. We'll try to understand it better. 2 alpha beta h squared over n. It has to be something that depends on alpha and beta, because after all, we were modeling the resonance with alpha and beta. So this curve is very famous. That's the distribution of the scattering amplitude over energies whenever you have a resonance. So we should plot it. If you have an E alpha, and you have an E alpha plus gamma over 2, and E alpha minus gamma over 2, when the energy minus E alpha is equal to gamma over 2, you get a gamma squared over 4, so the total amplitude goes down to 1/2 of the usual amplitudes. When the energy is equal to E alpha, you get 1. 1 for psi s squared. But when the energy differs from E alpha by gamma over 2, you get 1/2. So, actually, I'm not sure if the inflection point where it is. Probably not there. Or is it there? I don't know. I drew it as if it is there. So, that's the distribution. And the width over here is gamma. So it's gamma is called the width at half power or at half intensity. Yeah. Width, the half width of the distribution.